All right, everybody, so today we're going to be taking a look at stoichiometry, and specifically stoichiometry that's used whenever problems involve gases. Keep in mind that stoichiometry allows us to go from moles to moles of certain compounds. It allows us to go from grams to moles to grams, and so we're able to look at our products and our reactants, and we're able to determine the amounts that we need and that we use or that we produce. So in this example, how many liters of oxygen gas? So we're looking for volume of oxygen gas. How many form whenever this amount of KClO3 reacts? Assume that oxygen is collected at this pressure and this temperature. With these problems, for the most part, we're going to do in the order that makes sense. We're going to use the PV-nRT equation, and then we're also going to use our stoichiometric relationships at some point. So in this example, we are given that we have this many grams of the reactant. And so we want to know how much oxygen is formed. So in order to use the PV equals nRT equation, we need to have a gas, which would be our oxygen. And so we have our pressure, we have our temperature, we have our R, so we just need to have our moles. So how could we determine our moles of oxygen gas? The way that we can do this is by doing our stoichiometry problems. And so in this case, we're going to start with stoichiometry in order to go from grams of KClO3 to moles of oxygen. So if we were doing this and working on this, we would say we have 294 grams of KClO3. We'll use the molar mass to convert, and so in this case the molar mass is 122.55 grams per 1 mole of KClO3, and then we'll use our mole ratios, which in this case is 2 to 3, so 2 moles of KClO3, 3 moles of oxygen. And so at the end we would be canceling out our grams, our moles, and we would have 3.60 moles of oxygen. So our second step then is that we need to solve for volume of oxygen gas, and so we need to do volume is equal to nRT over P. So we're given P at 0.993 atmospheres. We have temperature 305 Kelvin, and our R 0.0821 liters atmosphere mole Kelvin. And then this is our N. So we'll go ahead and plug this in, 3.60 moles. And so we're left with 90.7 liters of oxygen gas from this problem. All right, so following a similar format, how about you go ahead and try to solve this? In a reaction, we have 4.58 liters of oxygen, so that's our volume. We have our pressure, we have our temperature, and we have our R. So in this case, we're trying to find grams of silver oxide, which is a solid. So we're going to start with PV equals nRT and solve for N. You'll need this conversion. After you've solved for N, then go ahead and do stoichiometry to do moles of oxygen, 2 grams of silver oxide. So go ahead and give it a try. So here's the work that you should have. Number 1, start with the ideal gas law. You'll end up with this many moles of oxygen. And then number 2, use stoichiometry to go from your moles, use your mole ratio, and then your molar mass. And you should have 82.3 grams of silver oxide. Now, if we're at standard temperature and pressure, this actually gets a little bit easier. So standard temperature, 273.15, standard pressure, 1 atmosphere. If we have 1 mole of gas, then the volume that it fills is 22.4 liters. Notice whenever you look here that even though the volume is the same, the mass will still be different because the molar masses of these are different. Now, the reason why it's 22.4 liters, if we plugged this into the PV equals nRT equation, then we would find that you get 22.4 liters. So let's go ahead and give this problem a try. We have 0.879 moles of calcium carbonate. It's going to decompose, and we want to find the moles of gas, or sorry, the liters of gas produced. So we're going to go from moles of, so we are going to go from our given. We're going to use our mole ratio. And then we're going to use our constant value, which is 22.4 liters of any gas, will be what the volume is of 1 mole. And so we would find 19.7 liters of carbon dioxide are produced. So go ahead and give this problem a try as well. So with this one, you'll start again with your given of 1.24 liters. You'll use your conversion factor, mole ratio, molar mass, and you'll get 0.998 grams of water. All right, now we're going to look at a more challenging problem. This one is going to require us to take a look at pressure if we collect a gas over water. And so the decomposition of silver oxide forms 15.8 grams of silver. So we want to know the volume of oxygen gas that's formed if it's collected over water. So our first step is going to be to do stoichiometry, where we're going to go from grams of silver to moles of oxygen. And then our second step is going to use PV equals nRT. Now, because we are collecting over water, then we have the pressure of the gas of O2 plus the pressure of the water vapor is going to equal the total pressure, which is what we are given here with the 750 SU. So this is the P total. So our goal is to calculate the pressure of the gas. And so this is what this looks like. We have silver oxide, it's decomposing. We're collecting the gas in this tube. So we're collecting the gas, and it's going into this water solution. And so then the gas is coming out here. So we have a combination of oxygen and water vapor, which will give us our pressure total. Okay, so this is going to equal our water vapor plus the oxygen. Water vapor will have a certain pressure based on the temperature that it's at. So in this scenario, if we go back, we were at 25 degrees Celsius. So the water pressure that we're looking at is 25 degrees Celsius. And so how this will work is that we have P total minus P of the water vapor will equal our pressure of our oxygen. So we have 752 millimeters of mercury minus our 23.8 millimeters of mercury, which will then equal 728.2 millimeters of mercury for our pressure of our oxygen. So you can use that and use the values that are given. So we have the temperature, you can calculate the moles, and we know the R to solve this problem. So if we look at how to solve this, again, we do the stoichiometry first. We find that we have this many moles of oxygen. We're going to have our pressure of oxygen, and then we'll convert it into atmospheres. Then we're going to have our R and our T. And we're going to go ahead and plug it into our PV equals nRT equation, and you should find that you have 0.935 liters of oxygen gas that are produced in this reaction. So we'll do a few more practice problems, but let me know if you have any questions.